another course, 5 lectures. We are very pleased to have Francisco Villaescusa Navarro, but he's Paco. So he's an expert on machine learning applied to very different topics. So let me say a few words about Paco. So he did his PhD at the Instituto de Física Corpuscular in Valencia. So he started as a particle physicist, maybe not, sort of. After his PhD in Valencia, in Spain, he was a postdoc at, at the Astronomical Observatory in Trieste. And then he was a Flatiron Research Fellow at the Center for Computational Astrophysics in New York. And then he went to Princeton as an associate research scholar. And he's now back at the Flatiron. He's a research scientist at the Simons Foundation in New York City. So it's a pleasure to have Paco, and he will give you the lectures on machine learning. I'm surprised that he's giving the lecture, and not a machine is giving the lecture, but...
Wait, I'm giving.
And he's also giving a colloquium on Wednesday on machine learning and everything.
So thank you, Rogero. Can you hear me well, right? Okay. So yeah, I mean, the purpose of these lectures will be a little bit more practical, so, really like coding. So if you didn't bring your laptop, is fine. Everything is, so basically, if you go to this website, like GitHub, basically my name, and ICTP-SAIFR, then you will basically find basically this repository where I will upload all the slices there, and there is the notebooks and also some data that we will need. So yeah, again, if you didn't bring your laptop or your tablet, is fine, but you might want to do this for other days. So yeah, so I'm just basically gonna go here to the slides and just basically have a very small introduction, and then I think we will be coding. We will try to, maybe use a very simple, fully connected layer today to train, just to give you an example. So, as Rogero was saying, Francisco and Paco is the same in Spanish somehow. I still don't really know why. In Brazil, you don't have this thing? Chico. Okay. Chico. Okay. So anyway, some of my colleagues, they always get confused. I remember one day one person is like, people talk about this Paco, but I don't know who this Paco is. I only know you, and it's like, okay. So, yeah. And so basically this is it. So let me just tell you a little bit, what is my idea for these lectures. So today, I'm basically assuming that you maybe don't have any background on machine learning, so I'm going to start, very, very simple, what is really machine learning. And, at the end of the day, hopefully we will be able to train like a fully connected layer, so a very simple model. For tomorrow, we will be using like convolutional neural networks. So, fully connected layer and convolutional neural network, these are kind of, I would say now, classical deep learning methods. Still people use it, but for instance, convolutional neural network is not even, I would say, state of the art anymore. So then, in Wednesday, I will be talking mostly about transformers and large language models. This is the time where Rogerio will start thinking, is like, why did he invite Paco for doing these things? But the idea of these lectures is that we will be using large language models, and as you will see later, this is really kind of a revolution that we are living these days. So, maybe this is the first time and maybe the last time that you will see this kind of background, how you train a transformer, how you train a large language models. And maybe you will never use this thing again, and we will, of course, not train anything like this here. But if you are going to use large language model, I think it will be good for you to have a little bit of background on this. Then on Thursday, we're going to do something that is state of the art. So we're going to basically code agents. And again, this is amazing. So we're going to basically code some agents, I believe, to generate ideas. Someone gives you some data, maybe this thing can generate ideas, and you will see later that this is really amazing. And then day 5 is really where we're going to have this really, in my opinion, spectacular. So my idea for this will be that we will write papers, like seriously. So, we will have some data, and we will try to see, and basically want to show you, the power of deep learning, of AI these days. reaching the point where, we might be able to write entire papers, maybe in 1 hour. So for this, we're going to use like the best models ever trained, by industry, like, OpenAI, Gemini. So at the end of the day, for using this model, we will have to pay. So that's why, we will just need a little bit of, I will not be able to pay for everybody here. So my idea will be to split in groups, maybe to have like 6 different groups, and then, within each group, we can maybe write some papers, if that's okay. So, yeah, we will be doing this preparation slowly, but for today, I thought that it would be good to just maybe split into different groups. So it would be nice maybe to have 6 groups, and I thought that maybe a way to split this in the month that you were born. So if you are born in January or February, you will be part of the red team. So I'm not sure how you will organize, but try to try to cluster into groups. And the only thing that I will need is, given the group, please choose a representative. This will be, anyone. You can choose randomly. It doesn't really matter. But it will be better if the person chosen has a Linux or a Mac, because we haven't really tested, for instance, in Windows, if this didn't work. So try to cluster, basically find a representative, and let's try to talk. Let's try to install the code that we need this, and I'm gonna give you like the keys to run these models. And yeah, so I think for today, just the only thing, try to cluster into the different groups. Any questions so far? Okay, so let me start. Can we pay a second?
Instead of paying the fee for the OpenAI, can we pay somebody to write the paper?
We can pay someone to write the paper. I don't think it's going to be as fast as writing a paper in 1 hour. And it's not really so much about writing a paper, but it's going to be really about how this thing can generate ideas, and some ideas will be original. Some papers are going to be very bad, right? So it's going to be like, this is like nothing. But being able to write all the codes, being able to make all the plots, being able to write the entire paper, this is really, in my opinion, spectacular. And we are in 2025. Imagine where we are going to be in a few years. So at the end of the day, yeah, we need to pay basically for the token usage. It's not really much. For every paper, it's going to be like $4, something like that. But of course, I think, yeah, I mean, someone will complain to me if I share my keys with all of you. Any other question? So, yeah, not sure if this works. So, okay, so let me just start. Okay, I think this maybe don't work. So, machine learning. So, you might have heard, machine learning, artificial intelligence, deep learning. So the first question is like, what is the difference between all of them? Oh, I think it's working. Yeah, thank you. So artificial intelligence, like the official definition, is basically systems that simulate intelligent behavior. And as you will see later, maybe on Thursday or on Friday, we are reaching a point in these kind of things where these things look really like maybe somehow smart. Machine learning is a subset of AI. That basically the idea is that it's going to learn to make decisions, by fitting some mathematical models to data. It's a little bit abstract right now. And then, finally, we have deep learning. So deep learning is basically just is a set of algorithms, and really what it makes them, let's say, different is that they use neural networks. So, in this course, I'm going to be basically focused in deep learning, but, there are other kind of methods, let's say maybe more traditional for machine learning, that still people are using them today, that you might be interested in this. So just two resources. There is this very nice book by Viviana Acquaviva, which is Machine Learning for Astronomy, that might be interesting for you. This is, I will say, more about classical machine learning. And if you are interested in really knowing a little bit more the details, maybe the mathematical details about deep learning, I will strongly recommend this book. So this book is amazing, it's super well written, and the book is basically free. You go there, all the book is free, but it gives you the slices, it gives you the images. It's really spectacular. So I strongly recommend you this book if you want to go deeper into some of the things that we will be talking in these lectures. Okay, so let me first start with, so how many of you are familiar with machine learning? How many of you have maybe done some project or done something? Okay, good, okay. So let's start with this. So what are the tasks that, for instance, you think machine learning might be useful for cosmology? Very good. Okay, so let's try to put all these things here. Yeah. So actually, regression is something that we're going to do in the lectures. Say again? For emulations, okay, yeah. Emulation, okay. Other things? Say again? Classification, yes. As we will see, classification and regression is kind of the same thing, but yeah. Say again? For calculus, but what do you? For labeling things. That's kind of a classification, I will say, probably, no? When you want to put labels into different.
Clustering.
Say again?
Clustering.
Clustering, yeah. So clustering. Okay, other things? Yes, that's a very good one. So redshift estimation, which at the end of the day, you can see this as a regression, right? You are trying to regress the other things. Yes, that's also kind of regression, but yeah, a little bit more, I will say technical, is to say that this is like inference. Inference is kind of like regression, but with error bars, roughly. Other things? So, I mean, there are many things. For instance, things that people have done is, for instance, accelerate simulations, or simulations, or for instance, you can accelerate inferences. You have some kind of NCNC, maybe you want to accelerate this thing. Other things? Exactly. So pattern recognition, exactly. So pattern recognition. Good. Other things? So for instance, I mean, something that I mentioned before these days, we can, let's say, this is still something very new, but let's say AI scientists, we can also do, for instance, anomaly detection. And, there are really many other things that can be done. So just to illustrate that, machine learning is very powerful, and this is not only really focused on cosmology, right? Please. So AI scientist is this thing that basically, you have some data, and basically this thing is able to analyze the data for itself, reach some conclusion, and basically write an entire paper. Which again is something very polemic, and if you go to the colloquium, I will be talking about this, and that talk is going to be mostly about maybe ethical considerations about these things. This is really in my opinion, a transformative technology, and I think society will change because of this. But yeah. Any other thing? Okay, I think this is a very good list. So Okay, so in machine learning, there are basically 3 different categories where you can basically, let's say, 3 different categories or methods. So one of them is like supervised learning. So supervised learning, the idea here is that you have some data, but very importantly here, the data has some labels. So for instance, this is a plot where I have points, and the points have some labels, and the label is the color. There are blue points, and there are like red points. And the idea of this method is basically to develop some kind of model where you are able to, if someone gives you now like a new point, you will be able to predict this label. So for us, for instance, in cosmology, imagine that I don't know, you are every point here, let's say, represent the power spectrum or something like that, any cosmological observable, and maybe what you want is to predict the value of omega matter, let's say. That's your label, and that's what you are trying to predict. Then there are other categories of methods that are called unsupervised learning, where here the idea is that you only have data, you don't have any label. And the idea of this method is basically to try to extract patterns directly from the data. So for instance, if someone gives you this data, you might say, okay, so yeah, this looks very nice, but what I can see is that, for instance, here, there is some kind of cluster, and maybe here there is another, or maybe this is different to this one. So the idea is basically to learn patterns directly from the data without having any label at all. And as we will see later, this is also the way that, for instance, we train large language models. We give a gigantic amount of text, and it's basically able to learn, the way that we talk. And then finally, there is reinforcement learning, where is something that I will not be talking in these lectures. The idea here is basically to tackle problems that are, let's say, more complex, right? It's like, imagine that you have some kind of machine, and you are playing chess, and the idea is basically to win the game. So you are not really interested in just predicting, given the, let's say, table, which is the next move, but really try to predict what are the ways that you will have to move your thing in order to win the game. So that's a much harder problem. And let me just say that machines are already better than us playing chess. They are better than us playing Go. Okay, so for supervised learning, which is the thing that we're going to try to focus today, there are mainly 2 different categories. So one of them is like classification, as we were talking. So in this case is when you have a discrete set of labels. So you can imagine red, blue, green, or you can say, okay, so my universe is lambda cold dark matter, or my universe is modified gravity. So discrete things. That's classification. The other one is regression, and is when you have a variable that is continuous. So for instance, if you want to predict the value of omega matter can go from, let's say, from 0.1 to 0.5, and it can take basically any number in between. Any questions so far? This is just basically like mostly terminology, machine learning, like the different, let's say, ways or methods. And now I would like to start going, for instance, into the simplest model for deep learning, like fully connected layers. Any questions so far? Okay. So let's start with a very simple neural network. So the idea here is, imagine that you have a problem where you have like 2 variables. So let's say that this is, maybe your variables are what is the temperature in Sao Paulo today, and maybe the other one is what is the pressure in Sao Paulo today. You only have these 2 variables. So this is your input, and the output here might be, what is the probability that it's going to rain today, right? So you have an input, and you have an output. And the idea of this thing is basically that, you might be able to write your output as a function of the input. That's at the end of the day what we really want to know, right? Someone gives you an input, you want to predict the output, and if there is a relation between these 2, there might be a function there. This function might be like very complicated, but there might be a function, okay? So you know, a very simple model to do this is what is called a multi-layer perceptron. And basically, this is a scheme of how this thing works. So I'm going to guide you through it. So you know, this is our input. We have two variables, x0 and x1. And again, imagine that this is, for instance, the temperature, and this is the pressure. So now here we have a layer. This is what is called a fully connected layer. Because basically, this neuron is fully connected with these ones. So each of these, let's say, circle is called a neuron. So for instance, this neuron is connected to the temperature and is connected to the pressure. So what this neuron is doing is something very, very simple. So you know, this neuron is basically doing a linear combination of the temperature and the pressure. You know, this is just like a linear, basically a linear transformation. And then after that, is basically passing the result. You know, this is going to be like a number. Once you do this, this is going to be a number. And then you are going to pass through this function. And this is going to be, in the next slide, we're going to show this. This is going to be a non-linear function. And this is very important. And that's what this neuron is doing. It's just, you know, taking the input, linear transformation, and a function. That's it. So, you know, this neuron is doing exactly the same thing, but with this and with this. And take into account that, you know, this neuron has some free parameters, this W00, W10, and this bias. These are free parameters in your model. You can imagine that these are parameters that you will later fit. And then, you know, in this neuron, exactly the same thing, right? This is the input, these two variables. So I'm doing a linear transformation, and I have some free parameters that I'm going to learn later. And then I do a non-linear transformation. Okay? So this is like the first layer. So now, in every neuron, I will have like a number, which is basically the result of doing these operations. So the next thing that we're going to go to the next layer. So now we have another layer with two neurons. And for instance, look at this neuron. So now this neuron is connected to three different neurons, to this one, and to this one. And that's why here we have three, let's say, three different values, and we have the different, you know, free parameters. But it's doing exactly the same thing, right? It's doing a linear transformation of the input to the neuron, and then a non-linear mapping. This neuron is going to do exactly the same thing. And then, you know, when we go to the last layer, again, you know, this neuron is connected to this and to this. So I'm going to do a linear transformation, and I'm going to put here, you know, some free parameters here. Again, the same thing. So this is what is called a multi-layer perceptron. And what is very beautiful about this, and this is at the core of deep learning, is that it has been shown mathematically that basically, you know, this kind of very simple thing is able to represent any function. You know, if you have any function as complicated as this one, there are some mathematical, you know, things like, you know, it has to satisfy. But in practice, basically any function with things like this, you will be able to approximate this. And this is really like, you know, at the core of deep learning. You know, it's like, if someone gives you data, someone gives you input and output, at the end of the day, you just need to fit for these free parameters. And you are kind of guaranteed that this will work. In the limit, well, in the limit, I mean, if the data, I mean, you will need data, of course. If you have very few data, it might not be perfect. And what else? And then, you know, the mathematical theorem says that, you know, you only need like one layer, but this layer needs to be in principle infinite. In practice, it's not infinite, but yeah. I mean, we will see later that, yeah, this thing really, to learn patterns, and this thing is really amazing. And yeah, please, please. Yeah, so this is a very good question. This is what is called hyperparameters. So for instance, how many layers you consider, how many neurons per layer, all these things are what is called hyperparameters. So there are things that in principle you should choose. Or you can use methods to tell you what are the optimal ways for doing this. But yeah, that's something that you in principle input. Other question? Please. Are the same? What do you mean? Yes, that's a very good question. So in principle, no, it doesn't have to be the same. I mean, I think in practice, for every layer, they will be the same, but different layers can have different functions. And at the end of the day, this is a little bit like a Lego block. Sometimes you play with this thing, and some functions work better than others. But yeah, it doesn't have to be the same. Please. This one? Yeah, so this is a very particular example. This is what is called the ReLU function, and let me draw it here. This is like the simplest nonlinear activation function. And what this function is saying is that if this is 0, your function is like this. And if it's negative, basically it's just 0. So you see, this is a nonlinear function. It's a trivial one, right? This is like y equal to x. But in practice, this is really the one that we use. I mean, I don't know these days, probably people have come out with something better. But this is, yeah, and it's called ReLU, that it might be familiar to some of you. Because it's like, it's kind of, you have this input to the network, to the neuron. And for instance, if you are using this, and imagine that this operation that you do is negative, then the value of the neuron will be 0. And I think this is what historically people say, okay, the neuron is not activated. So you will have, values that can be large, and some values will be 0. So I think that's where it comes from.
Sigma is another question.
Exactly. I think, let me go to the next slide. So in practice, this is kind of like the different activation functions. Sigmoid, exactly as you were saying, is a very widely used, and this thing changed a lot. When I was a student, I think this was not very popular, but I think now people maybe use it more for transformers. So, it's something that changed very rapidly. ReLU, this is the one that I was saying. I think this is like very good, and many people use it. But just to say that there are many others in the market, and yeah, in practice, how well this works for your problem, I think you need to try. Yes, it could be very different in the performance, yeah. Yep, unfortunately, yes. My experience is that, if you use ReLU, you will be fine. But, if you are trying to get the best, accuracy, maybe you try with this one and it gives you 10% better accuracy, something like that, yeah. So it's very problem dependent. Any other question? Yes.
So I've been working with machine learning for a while, and when it comes to a recurrent neural network, I was just wondering, if you take, for example, the first layer, the X11, in this case, it's a fully connected layer, so it's connected to X0 and also X1. When it comes to a recurrent neural network, so that means that X11 is also going to be connected to X10, or that does not make any sense?
Yes, so recurrent neural network, of course, much more advanced than this. I have to remember, so if I remember correctly, with recurrent neural networks, you have, let's say, your state, let's say you have your input, and then it gives you like an state, and then this is something that you pass, right? It's something like that, if I remember correctly. So I will say that from what I remember, but I might be wrong with this, I think the input state is not something that you transmit along these things. You pass into the model will update this state that it has, and this is something that you will be passing.
Okay, so
No, I don't think so. I don't think so. But we should probably talk later more in detail, just for me to remember all this detail. But yeah, I think that's not the case. Other questions? I think we are almost, yeah, please. Exactly, exactly. So let's go to the next slide. Well, just give me one slide. So the exercise that we're going to do today is the following, just to illustrate this. So we will have data for, these are full hydrodynamical simulations. This is a little bit what David was talking this morning. And in this full hydrodynamical simulation, we have some data that is called the star formation rate history. I think this is basically is the amount of stars per unit of time that you produce in a given universe. And our task will be basically to see if we're able to constrain the value of the cosmological parameters, just given this data. You know, as far as I know, this is a super weird exercise, right? I don't think anyone in practice has done this thing, you know, like taking the star formation rate and try to infer cosmology from this. But you know, we will see that at the level of simulation, this works. So the first thing that we need to define is basically what is called the loss function. So the loss function is really what we are going to really optimize. So, you know, we will have a model where it's going to take, you know, the star formation, you know, basically imagine that this is the input to our function. It's basically the star formation rate history for different redshift. So, you know, this is maybe redshift 10, redshift 9, redshift 6, whatever. And, you know, given this data, we're going to try to predict, let's say, omega matter. So, you know, how well we are going to do. So we're going to define this very simple, let's say, loss or cost function, where we're going to say that, you know, this is the true value of omega matter, and this is the predicted value of omega matter from the neural network. So what you can see is that this function, the only thing that it's doing is that, you know, if the neural network is able to predict something that is very close to the true value, then this thing is going to be very small. But, you know, if you predict a value of omega matter that is very different to the true value, then this is going to be like a very large. So the whole game here will be basically that we are going to try to optimize, you know, minimize this loss function. So remember, this loss function is a scalar quantity, it's a number. So our whole game here is to make this number as small as possible. That's really the goal. How we do this in practice? Coming back to your question. So we're going to use an algorithm that is called a gradient descent. So imagine that, you know, this is our value of omega matter, you know, this theta, and this is how our loss function look like. So imagine that this is some kind of parabola, okay? So let's say that, you know, we're starting at the beginning. You know, at the beginning, all these free parameters of the network are completely random, right? So you don't expect this to be very accurate. So, you know, you pass your data into the model, and the model, it might tell you that omega matter is here, whereas let's say the true value is here. So you see that this was like a very bad prediction. So what you do is to say, okay, fine, but then what I'm going to do is basically I'm going to compute what is the value of the loss function in this particular point, but I am also going to compute what is the derivative of the loss function with respect to the parameter. And you know, in practice, we have thousands, millions, billions, trillions of parameters. This is a little bit the magic also of deep learning. We have really like very good ways to be able to compute the derivatives for every single parameter. And then the idea here, please. Yeah, sorry. I think it was confusing. Yeah, so this is like one of these, let's say, W that I was putting at the beginning. Yeah, sorry. Please. How do you define the loss function? So the loss function is basically just given by this. Why? I mean, you need to define some kind of objective function that you want to optimize. And I mean, what you want at the end of the day is to make the network to be as precise as possible. So this is, for instance, a good function that satisfies this. If the prediction of the network is close to the true value, then this is going to be like a good model. You can define, there are many other ways to define the loss function. But in practice, this works very well. Please. No. Yes. So for instance, we will not be doing here inference, but if you want to do, for instance, inference, something that you might want to do is basically try to learn directly the probability distribution function of, let's say, your parameter. And in that case, what you will be learning is like the distribution. You don't learn a single value. You learn the entire distribution. And again, because fully connected layers can approximate any function, they can also approximate your, let's say, posterior or your likelihood. What do you mean? Yes. But you might learn the likelihood directly, no? I'm not sure if I understand. When it's not a likelihood, you mean like when you have the, sorry, I'm not sure if I understand you, Ricardo. No, but I mean, in principle, you can learn any function. If it's a likelihood, it's fine. If it's the posterior, it's fine. But if it's any other thing, it's also fine. But maybe I'm not understanding you. Let's talk later. Okay, so it's clear like why we use the loss function. Okay, so, at the end of the day, this is really the whole trick. It's like, for every parameter, in principle, you will be able to compute the derivative, the partial derivative. Let me write here. So basically, you are able to compute, let's say, the derivative of your loss function with respect to, in this case, will be like the weights that we were defining before, not the theta. And the trick is that, you can update the value of every weight, of every free parameter, just given this very simple, let's say, equation. And what this is telling you is that, so for instance, the derivative in this point is positive. It goes like this. So what you want to do is to move in this direction, right? So that's why here we put a minus sign. We have, let's say, the gradient of your loss. And this is what is called the learning rate. And this is a very important thing. It's a hyperparameter. So for instance, imagine that this learning rate is, how much you are moving from this point. So, if the learning rate is very small, you will be moving from here to here. And then, in the next step, you will be moving from here to here, and, maybe in 3 weeks, you will arrive to the minimum. With this learning rate, it's very nice because you can see that it goes very small. But also, if the learning rate is very large, you might imagine that you can overshoot. So, imagine that you take a very large learning rate, so you might go from here to here, and then, you will never basically converge. So, choosing the learning rate, this thing is also kind of, I mean, you need to basically play with these things. But this is basically the idea. Please. No. Mm-hmm. Yep. Yes. Yeah, I mean, if you are in a supervised setup, I mean, you are already assuming that you have a label, right? Somehow. So for instance, if you are using simulations, you will know the true value of the cosmology. If you are in a unsupervised setup where you don't even know the true values, then what you can do is unsupervised learning, right? But of course, imagine that if you have some data and the data doesn't have any labels, I mean, even in that case, you might be able to put labels with this unsupervised learning. You might be able to see that there are clusters, like, for instance, prediction from modified gravity are really different to the prediction from lambda CDN. But given that, you might still not be able to predict, let's say, the true value of the parameters. That's very model specific. You need a model and you need the labels. If you are in a supervised setup, you need labels. Labels. So let's put, like for instance, an example. So let's say that my task is going from, let's say, the power spectrum, P of k, to the value of, let's say, omega matter. So, in this case, what you will say is that, omega matter will be a function of the power spectrum. So let's say, I'm going to say, so this is P0, P1, P2. So, this is the power spectrum for the different case. So, to solve this problem, you will need different power spectra and the corresponding value of omega matter. So this is the label. Given a power spectrum, this is my label. You will need this. If you only have power spectra and you don't have any model or anything, I mean, you might be able to find classes, but I don't think you will be able to predict this directly. Any other question?
Why would you choose a layer that's fully connected instead of a layer that's not fully connected? Is it just a matter of performance?
You mean between a fully connected and something that is not fully connected? Yeah. Or you mean like not, for instance, not connecting this with this one? Yeah, sometimes we do this. For instance, in transformers, this is a little bit what is called the mass, and we will see this in detail. But if you don't have really any restriction, in principle, what you want is to connect everything, because otherwise, this neuron might not have information from these two things that it might be important for some reason. So you might want to, always extract as much information as you can. If you put the weights to zero, and even if you put the weights to zero, well, even this bias, then this will be a super weird, right? You will always get zero. Yeah, no, I don't think that will work. Usually the way that we initialize these weights, I think is like a random Gaussian distribution. I mean, there are even papers entirely written about how you should initialize these things. Yes, absolutely. I mean, many neurons in practice will have this zero value. So this is sometimes what is called, I think, the dead neurons. This might be a problem because, to compute gradients, if you have zero, basically the gradients will also be zero. So, but, we know that this happens. As long as you put enough neurons, this should be fine. And this mathematical theorem proves that you will be fine. Yes, so in practice, let me put it here. What we do is something like this. So, you will plot, let's say, the value of your loss function. And here you will basically plot what is called the epoch. So, epoch is basically how many iterations you are doing, roughly. So typically, the behavior that you see is that, initially the loss function is very high, and it's going down, right? Initially, it's learning, usually very easy to learn simple things. And at some point, you will see that, everything plateau, and it's like, okay, maybe this is what I should stop. I'm not going to talk about this, but, something that people have discovered is that it might be like this, and at some point, it do like this. This is it's called double descent, this thing, and I'm not going to talk about this, but sometimes things learn at some point for reasons that we don't fully understand. Please. Yes. In practice, it's basically the same idea. I think that, you are completely right. Exactly, exactly. In reality, it's really the same idea. I mean, NCNC is really more about sampling the distribution. In this case, we care only mostly to go to the minimum, not so much about learning the distribution. We just want the best value, right? That's the best model, and that's the only thing that you care. But it's the same philosophy. Okay, so any other question? So we have, Rogerio, until 5 or 5:30, just to 5. Okay, perfect, yeah. Okay, so I think this is probably my last slide. So, we have seen that this is really the way that you update the weights. And let me just say that, how do you compute these derivatives? So remember, these are the derivatives that we compute for every weight, for every parameter in the model. So, what do you think will be like a good way to compute this derivative? Will you compute, for instance, using all the data that you have? So imagine, for this case, will you evaluate the network in all the power spectra to predict omega matter? Yes, but it's not that the reason. So the reason is basically because, if you use all the data, your derivatives, I mean, if you compute all the data, the derivative will be computed, let's say, perfectly, right? It's like, this is really like the derivative, and that's it. So the problem about this is that, the derivative is going to be like a very smooth function. And when you have a smooth function and you end up in a local minima, you might be there forever, right? You might be trapped. Imagine that you have, I don't know, some kind of landscape that is like this. And if you are here and you compute the derivative is 0. So there is absolutely no one in the world who is going to take you out from this. So that's why in practice we don't do this. The other thing that you can say is like, okay, I'm going to just compute the derivative only using like one power spectra, one power spectrum, not all of them. So then the derivative is going to be noisy, right? And the problem about this is like it's going to be like too noisy. It might take you like a very long time. So in practice, what we do is something that is called, I think it's called maybe batch stochastic gradient descent. I forgot the name. But it's like, you will take like some samples about it. It depends on the problem, but typically, maybe 16, 32, or 100. It depends on what you are doing. And, what this is going to guarantee is that, if you are in a local minima, but you are not using all the data, you might still be able to get like a gradient here. So you might be able to leave this point. And still, because you are not only taking like one sample, it's still very computationally efficient. So, just the last thing, this is like a very nice example that is just for you to remember. I think you will probably remember this. It's like imagine that you are trying to go from New York to LA, and you are driving, and somehow you are drunk, right? So you should think about this. It's like, you are drunk. It's like, okay, I think LA is that way. But then you go like that, right? And then you go there and you go to a bar. It's like, oh, where is LA? It's like, oh, no, you have to go there. And then you go there. So, it's like you are doing this super weird thing, but at the end, you will end up too in LA. So that's exactly the same thing that we are doing here. We're not really going straight. We are doing these kind of things. And, this is very good because, you prevent these kind of situations. Is that clear? This is, yeah. All right, so I'm going to skip regularization. Otherwise, I think we will not. And let me just mention the data that we're going to use. So these are just some simulations whose data we're going to be using. So this is, for instance, one example of a full hydrodynamical simulation, state of the art. What you can see here in blue is the gas density, and what you can see in red is the gas temperature. So you can see all these explosions going on. These are either, supernovae exploding, or maybe, supermassive black holes releasing energy. So within this CAMOS project, we have like thousands of these simulations. This is the largest set of simulations ever run. And we're going to be using data from these simulations basically to do this exercise. So the exercise is going to be to take data for, let's say, every simulation. So for every simulation, at a given redshift, we know what is the star formation rate history. So basically, how many stars you are forming at a given redshift. So that would be our, let's say, cosmological statistics, observable. And the goal will be to basically predict the value of the cosmological parameters. Let me just show you this other movie. I just spent way too much time doing these movies. This one in particular, I didn't do it, but yeah, I always show these kind of things. So you know, each of these simulations is like, you know, very computationally expensive and, you know, whatever. So the nice thing about here is that, you know, you have like thousands of different universes, you know, and every different universe, you have a different value of, let's say, omega matter, you have a different value of sigma 8, but also you have different values for, you know, how efficient supernovae release energy, or how much energy supermassive black holes release energy, and these kind of things. So just let me show you this view. So this was like one universe. Imagine that you have like different universe, you know, each of them, they look like very, very different. And the goal will be to basically, for each universe, predict which one is easiest. Yes, please. Well, depending on how many cores you use, but I don't remember. I don't think this was very expensive. I think this is 5,000 hours per simulation. This is nothing. All the data is public available also, if people want to use it. And we have everything on Binder and Globus. So, you know, we have like 2 petabytes. So, you know, if people want to use it, you don't even need to download. Any other question, or should we start coding? Okay, so let's go to the coding. So what I'm going to do is basically come back here, and I'm going to go to this link, like notebook 1. Okay, so how many of you have used like Google Colab? Okay, so almost everybody. So as you know, the nice thing about this is that, Google basically give us the resources kind of for free. We can even use like GPUs. And I think we should maybe for this case use GPUs. So let me just show you how to choose. So if you go here to runtime and you change the runtime type, here these are the options that Google allows you. So you can use CPUs, you can use GPUs, or you can use TPUs. I have never used TPUs, but you can also train neural networks with them. So I'm going to use GPUs. And then, we are going to be doing this with PyTorch because that's the language that I know. There are, for instance, JAX is another one. TensorFlow is another possibility. So how many of you are familiar with PyTorch? But when I say if people are familiar with machine learning, there were like less hands. So how is this possible? Okay, so very good. So then, this will be like, I think, very easy for many of you. So I'm going to go a little bit fast. If anyone has problem, please come back to me later. So we will focus on training the neural network. So, this is really the way that you load the library. So let's say I'm going to run it. So we're going to just, import Torch and import NumPy. And, I think you should really think, if you're not familiar with PyTorch, PyTorch is basically like NumPy, but with GPU access. And, it allows you to compute also derivatives, but that's pretty much what it is. And, something that we're defining here is, for instance, defining a tensor. And this is really the same way that when you define a NumPy array. So, you have like 3 values. You can, for instance, this A is a random variable. This is in a NumPy array. You see, this is NumPy random. And then, you can do all kind of operations here with this thing. You can declare that this is a tensor. You can specify the type. And, I mean, there are really a lot of things here. You can just execute it. Yeah, again, if you have any question regarding this, please let me know. I'm going to go a little bit fast because I don't think it's particularly important, this thing. Yes. Oh, yes. Yes, thank you. Better like this, right? Okay. So, yeah, you can just execute these things, and it's going to basically print the values. It's going to tell you the type. In this case, it's a float 64. When we define with this case, it's going to be like a float 32. We care about this thing because, most of the things that we train neural networks, they are trained on single precision. And actually, people in industry, they train in half precision. I think even now they have like 2 bytes, something like that. So just let you know that for most practical applications, you don't need variables with a super high accuracy. Neural networks are not, I will say, maybe so precise. Yeah, please. What do you mean by shared data? Oh, I see, yeah. Yeah, so in some cases, from what I remember about this, is that you have your variable A, and this is the variable that is defined in, as an NumPy array, and either you can make a copy of this, or you can just share the object. It's like, this is really the same object. I'm not really duplicating. I'm not increasing my memory. I'm just saying, okay, this is really the object. So the way that you do this is basically the difference thing. But again, it's not very important. Okay, so let's see. Yeah, again, these are basically things that you can print information about the shape, the type. It's exactly the same thing as when you do this with NumPy. And yeah, I'm gonna skip this thing. You can, if you want, you can take a look at this notebook later in more detail. I think the only thing that is maybe important here is about this thing. How do you move data from the GPU to the CPU or the other way around? So, here in PyTorch, you can define the device that you have. So, by saying this, you are saying that CUDA is available. And basically, it means that, you are using like a GPU. And, in practice, if you're going to train something that is kind of heavy, GPUs is really the way to go. CPUs are much slower, and yeah, GPUs are really the way to go. So this is the way that you can define the device where you are using this. And then if you have some data, for instance, here I'm declaring just an NumPy array, and I'm saying this is an NumPy float. And now I'm moving this data into a tensor from PyTorch. And now what I'm going to say is like, I mean, when I created my data, I created it on a CPU, right? If I don't do anything, the data is really created on the CPU. And you will see that, when we print this, it's going to say that this is still in the CPU. The only thing that I have done is taking my NumPy array and just say, okay, so now you are a PyTorch array. But I haven't moved the data. If I want to move the data to the GPU, then I basically need to do this. I just need to say to device. And now this data is going to be on the GPU. And if you're going to train these things in practice, you have to be careful. The GPUs have some limited memory. You cannot just take all the data and move into the GPU. It will not fit in memory. So yeah, these are things that you need to take into account. So just printing this, you can see that the data was created in the CPU. And then, the data was moved later to the GPU. That's why it's in CUDA. And then I think we move later to the CPU by doing this. Okay, nothing really important. Okay, so this is like the first notebook. Again, you can go later by yourself, but it's really just like the basic usage of PyTorch. Any question regarding this?
What's better for GPU, just or
Depend on who you ask, and I'm being recorded, so I cannot tell you my personal opinion. No, but I mean, JAX is of course very good. PyTorch is very good. I think people say that JAX is maybe more optimized for these things, but I think there is less code maybe available. So, yeah, I mean, okay. So let's try to go to the other notebook, which is the one that why I cannot go back. Yes, leave. Okay. So now we are going to go to the second notebook. And as we were discussing, the idea here will be to use data from camels. And our task will be that, given the star formation rate history from these different universes, we have like 1,000 different universes, try to basically infer the value of the cosmological parameters, in particular, I think omega matter, just given these, let's say, summary statistics. So you can run this with me, or you can do this later. I'm just gonna. So the first thing that we need is the data. So for the data, what I'm gonna do, too many sessions, but I only have one, no? So let me kill this one. Okay. So what I'm gonna do is first just to upload the data. So why is saying that this is not? Connecting to a runtime. Okay, so I'm gonna connect also here. You have to, second. I have to run as.
Yeah, you have to run the cell so you can mount the drive.
Yes, but I think
You're trying to look for a file, right?
usually here it will appear like something to load, but okay. So you see here. So what I'm gonna do is basically just to upload the data. So the data is also in the GitHub repository. So I'm gonna come here. I'm going to data. And these are basically the 4 files. And we're going to look at them. Okay, so yes. Okay. So now the data is here in Colab. So I put this line here. This is basically because, you can, you can either upload the data as I'm doing, but if you have really like a very large amount of data, you might want to use, for instance, like Google Drive. So you can upload the data to your personal Google Drive, and this is really the way to do it. I mean, I'm not going to do this because I think we don't need this. But yeah, if you need, if you have like a very large data set, this is the way to do it. So, okay, so let me load the libraries. Here I'm just basically uploading the libraries. And then here, we're going to say, are we using GPUs or are we using CPUs? And it's saying that CUDA is available, so right now we're using GPUs. So first, let's take a look at the data, right, to see how this looks like. So the only thing that I'm saying is that, the redshift are going from 0 to 7. There is like 100 values. This is just basically the data that I have. And, this is really the way that we arrange these things. Then the next thing that I'm going to do is basically load the data itself, this star formation rate density, I believe. And this is this file. So I'm just basically loading the data. And the other thing that I'm loading is the value of the parameters. In this case, is cosmological parameters and astrophysical parameters. Okay, so I'm just executing this file. And now let's take a look at how this thing looks like. So for instance, you can see that the redshift is just an array with 100 values. But the star formation rate history is basically a matrix where we have 1,000 different entries, every entry for a different universe. And then in every universe, we have 100 values, which is basically for every redshift, we have the value of the star formation rate density. And then for this thing is basically the value of the cosmological and astrophysical parameters. So we have 1,000 entries, one for every different universe. And then we have 6 numbers. So in this case, we have omega matter, sigma 8, and then 2 astrophysical parameters, 2 supernova parameters, and 2 AGN parameters. It doesn't really matter, these things. But in the simulations, we vary these things. So, yeah. OK. So we can plot, for instance, so what I'm doing here is basically just plotting, for instance, the first star formation rate density. And this is like the second one. So if I plot this is what I see. So you see, this data is, this is redshift. We go from 0 to 7. And this is the star formation rate history. And the units here is like solar masses, how many stars you are forming in solar masses. And this is like per year, and this is per megaparsec. So this is telling you is like how many stars you are forming, like the density, per volume, but also per time. It's just the way that is. These are just for 2 simulations, exactly. We're just plotting this just to illustrate. You can change, you can maybe plot the third one. It's going to be different, and yeah. So this is how this data look like, right? This is like maybe a bit weird thing, right? It's like, who will use this to constrain cosmology? So, well, we'll see. So everything that we are assuming here is that given each of these curves, there is a function that relates then to cosmology. That's our only assumption. And what we're going to try to do is to use these fully connected layers to learn that function. Okay? And that's just measured from the simulation. You go to a simulation, you measure this, you have the value of the parameters, and that's it. That's your data. Any other question? Okay. So what I'm plotting here is just, how does, for instance, for simulation 0, which I think it was like this, maybe like one of these lines. So in this case, the value of omega matter is 0.3, the value of sigma 8 is very large, is 1, almost 1, and then, these astrophysical parameters has other values. And for simulation 1, this is the value of omega matter, and sigma 8, and these other ones. Just to see, how things look like. So, say again. Yes. So let me write here just to tell you exactly what we are trying to do. So let's say for a given universe, so this is redshift, this is this star formation rate density. We might have this weird thing, okay? And we know that for this universe, the value of omega matter, let's say, is like 0.3, okay? So what we're trying to do here is like, we're saying that omega matter is basically a function of this star formation rate density. So let me call this, let's say this point here, this is like S1, so this is like S1, this is S2, S3, blah, blah, blah. So this is our problem, right? Given this data, given this function that I sample in this particular redshift, I want to constrain, I want to regress, in this case, the value of omega matter. There is a function that I don't know. This will be something complicated, but I'm going to basically train a neural network to learn this thing. Is that clear? Sorry. Yes. So in this case, our input is the star formation rate density. This is our input, and our output will be omega matter. So the idea of this is like, you train your model, and now, we go to another universe where a different cosmology, where this thing is doing something like this. We will be able to take this function and say, okay, so this universe, the value of omega matter is this.
So not separating your data set and learning data set and then test?
Yes, we're going to do this, of course. You need a training, validation, and testing set. Yeah. Yes, right now we haven't split the data. Right now, yeah, we are just showing everything. Please. Yes, so that's a super good question. So in this case, the way that this works, the nice thing is that even if you simulate universes that are completely has nothing to do with our universe, in principle you don't care, right? Because at the end of the day, you just want to learn this function, and whether this is learning things that are not really real, you don't care. So in practice, what you want is that within all your simulations, there will be somewhere that is going to be reasonable. If all the simulations are wrong, yeah, this will not work. But in principle, you don't care to simulate things that are completely out. Any other question? Okay, so let's try to finish this in maybe 10 minutes. Okay, so what I'm doing here is basically just setting the value of the hyperparameters and just saying that this is my file that contains the star formation rate density. This is the file containing the value of the parameters. I'm just saying that my batch size. This is something that we were discussing before. Is like how many examples do we take to compute derivatives? I'm just setting this to 32. I'm just saying that the value of the learning rate, how fast we're going down this curve, is set to 3 times 10 to the minus 4. And then, there are other things here that are not very important, but, I'm very happy if you later want to know about these things. So, we can this is just setting the value of the parameters. This is the same thing that we were discussing before. We're going to use the L2 loss function, basically the mean square error. Please. Yes, absolutely. If you train for a very long time, I think you will overfit maybe at some point. Well, it depends on the capacity of the network and these things. And just put in 300 so we can finish in 10 minutes. But yeah, I mean, you can play with these things. It's really trial and error. Usually, this is kind of, I would say, a good value for fully connected layers, but in practice, you need to play with these things. Yeah, one is not a good idea because, I mean, the learning rate usually is something that is much smaller than 1 because it's, how fast. I think if you put to 1, you will always overshoot. So typical values is, I don't know, 10 to the minus 2, 10 to the minus 6. It depends on the problem. Okay, other questions? Okay, so if not, what I'm doing here is what Rogerio was talking. I'm just basically dividing my data set into, into training, validation, and testing. So this is something very important, and I didn't mention this before. So, when we have data, we need to have different sets. If we have a model and we train on that model, and that's really everything that we see, we might be overfitting. Your model might be just, learning, memorizing the data. And, if you don't have any other data to check if your model is good, you might say, okay, my model is amazing. But at the end of the day, you might just be really like, learning the data. And if you're memorizing the data, when you have new data, it's not going to work very well. So that's why, in practice, what we do is like we have all the data, and we split into training and validation. And what you do is to say, okay, so I'm going to train my model using my trained data. And while I'm training, I'm going to evaluate how well the model works on the validation set. So the validation set is basically something that you just use to quantify the performance of your model. But on top of this, you have what is called the test set. And this is like very important. I just want to, if this is the first time that you are learning this thing, the test set is really supposed to be like, you should never look at it, right? This is like, should be like prohibited, you should never look at it. And, the idea is that, you might still overfit in the validation set. Because the way that you will say, okay, this is my best model, is you're going to say, okay, so I'm going to choose the best model to be the model with the lowest validation error. And by chance, you might also find a model that performs super, super well on the validation set, but still, might not perform very well. So that's why, it's very important to still have like a test set where you should never, never, never look at it until you say, okay, this is my model, and now I'm going to test on it. Yes? Yes, so in practice, there are different summary, let's say, estimators. The mean square error is one of them, but people use, depending on what you are doing, right? If you use inference or classification or other things. But if you are doing, let's say, in this case, regression, people use the mean square error, the R2 is another statistics, mean relative error, things like that. So, usually they are very correlated. But if you only look at one of them, you might not be fully, yeah. Okay. I think it's fine also if we continue tomorrow. We don't have to finish or... So we have 15 minutes, but it's also like with questions or... They might be tired of me if I will stay like 2 hours here. No, let's do maybe 5 more minutes, and we can continue tomorrow. There is really no. So what this function is really doing is, we can look at this. It's reading the data. In this case, it's reading the star formation rate. It's reading the value of the parameters. And now it's doing basically some normalization. I'm basically taking the log. Because if you remember, well, in this particular case, there are not so many differences, but you can see that there is almost like a factor of 10 from the minimum value to the maximum value. So, when you have like big differences, sometimes for neural networks, it's a little bit difficult. So that's why, if you take the log, you will basically reduce the dynamical range about this. And then, the only thing that I'm doing is saying that, my data normalized, I'm going to reduce the mean, and I'm going to divide by the standard deviation. That's something that we use in machine learning. Is very, very common. It's called normalization. And in practice, it has been shown, and there are reasons for this, that if your variables have a mean 0 and a standard deviation of 1, roughly, things like that, they will train faster than if you have a mean of 30,000 and a standard deviation of 1 million. It will take a very long time to learn these kind of things. And then, for the value of the cosmological parameters, exactly the same thing, right? Just reading, computing the maximum, the minimum, and normalizing them. And then this is just like a splitting the simulations. Okay, so nothing in particular. And here I'm just creating like a, let's say, like loading, like a data set, a loader for each different one. And again, you can run this notebook if you want later. Everything is in the repository. And this is really the way that we define our architecture. So this is important. So, this is an architecture where I have basically 2 fully connected layers. So, I have, this is like the way that you define this. So you have a fully connected layer where you have a given input size. So you should think about this like, maybe you have here like 3 neurons. So the input size here will be 3. It's basically the number of neurons. But maybe you have now a layer with, I don't know, let's say all these neurons, 1, 2, 3, 4, 5, 6. So the number of layers there will be 6. So the output will be 6. So this is just what you define here, like input size and this hidden size. So what I'm doing is basically say, if this is our input size is 3, and our hidden size is, let's say, 10, this is something that you choose, right? Is how many neurons do you want to put in that particular layer? So what I'm saying is that I have a layer that goes from 3 to 10, and then I have another layer that needs to go from 10 to my output size that is, let's say, 1, because we are only predicting omega matter. That's it. Please. Yeah, so this is really, as we were, there is no guidance about this, exactly. So if you remember, we were choosing here, no, let me see. So I think maybe we do this later. I think, sorry, let me look at this. Where is written the hidden dimensions? But this is something that we need to basically input to the model. So let me just make sure. Okay, so here, for instance, yeah, we use like 100, 100, and the output is 6. So yeah, as you say, there is really no guidance. There is no theoretical reasons that you should choose 123. In practice, I mean, if you do this by hand, it's super boring, right? I remember in my early days, it's like, oh my God, I hate deep learning. I choose 100, 101 was better. So in practice, the way that we do is we use something that is called a hyperparameter optimizer. That is basically, you start from some initial values, and you can basically optimize this self. Also, basically finding like a minima for this landscape. So it's an optimization of an optimization. It's going to take longer, but it works very well. So in practice, yeah, you don't have to do this by hand. But as far as I know, like the big models, things like ChatGPT and these things, I'm not sure if they are even can do like hyperparameter tuning. I mean, this is maybe too expensive to do them. So they just basically, they train with some values, and as far as I know, might be wrong. All right, so yes. Yes. In practice, yeah, I mean, it's a little bit related to this thing that we call the double descent. We can discuss later a lot about this, but yeah, there is usually not a problem if you have more parameters than even data. You might just be overfitting at some point, but this is like this behavior that, as you increase the number of parameters, you might think that, at some point you overfit, and that's it. And, the more parameters that you add, you will never improve. So that's not true. That's this phenomena, and again, this is a fascinating thing. If you keep adding parameters, you will see that your model at some point might do even better. So, in the very old days, I remember, it's like, there was this philosophy, it's like, use always the smallest network that you can to train your model, right? Don't put too many things because you will overfit. These days, it's the opposite. It's that put as much as you can. Don't worry, you will be fine. And we can talk later about this thing, but this is a fascinating phenomena that happened, that people observed a few years ago. Maybe this is a good time, I don't know, Rogerio, because I think it will take us more than 5 minutes to finish.
So you're keeping us in suspense to see if it works or not.
It works. You can run on the, yeah.
So more questions for Paco? Yes.
Thanks for the lecture. I would like to know if you know some kind of machine learning model or AI model that you don't depend too much on the representativeness of your training data, because in cosmology, like for Redshift, the biggest problem is that your training data is not representative to your application data. And do you know, like, in your head, if there's a model that is better when you don't have all that representativeness than other models?
Let me see if I understand the question. So you are saying models that generalize better to data that you haven't seen or something like that?
Yeah, because there are some models that do very poor if your training is different from your application and others like is like better?
Yes, exactly. No, that's a super good question. Yeah, this is I mean, it's an entire phenomenon. It's called out of distribution. There are an entire field working on this. But yeah, it's very well known that if you train a network using some data and you test this on data that is very different, in principle, it will not work. So there are ways to mitigate this thing. There are, for instance, things called domain adaptation that is basically try to bring the two different data sets. For instance, one example is with this data, simulations. As I showed you this beautiful movie, this is state-of-the-art hydrodynamical simulations. They are able to reproduce many properties in the real universe. Still, this is not the real universe, right? So if we train a model using these simulations, I think we have still, very, I think the expectations that this might just work in the real universe should not be very high because, our simulations are still not the real universe. So we expect differences into this. That said, there are many methods to basically tackle this thing. And yeah, I think that's...
Okay, thank you.
From your code, I see that for each layer, you use a different activation, right? Is there a reason for that?
Let me see. Yeah, you are right. I'm using here ReLU. So let me see. So here I'm just having like the fully connected layer, then I'm passing to the leaky ReLU, and then I have the dropout. So in this particular case, I'm only using like leaky ReLU, even if I have this line here. But in principle, yeah, as I was mentioning, you can play with these things. You can change the activation layer for every different layer. And yeah, there was no reason. I mean, in this case, was just as an illustration.
I didn't understand how to calculate the loss function if we don't have the true value of the parameter.
Yeah, if you don't have a true value, you cannot compute the loss function, at least in this setup. So this is like, we're doing this in a supervised learning machinery, let's say, manner. So you need to have labels. If you don't have labels, there is no way that you can compute this loss function. So in this case, because the data is coming from simulations, we have the labels. The labels is the value of omega matter that we know for every simulation. That's a good question.
My question it's more general question about the classical machine learning methods. Because, for example, in this example, we test, we training, validation, you shuffle and in the end you can choose one accuracy method to see how great is your fit, but how we can estimate the uncertainty for your models or your parameters. For example, if we try use supernova data, we have the one matrix for the uncertainties and have correlation between the points in the data. And when you use the classical machine learning, you only say the features. Sometimes you can include the covariance matrix in the loss function, but this is not propagated for your output. And how we can do this?
Yes, so that's a super good question. So for everything that I've been talking here, we are doing like regression. And yeah, I'm assuming that basically there is no error bus or anything like that. So there are several things. If what you want to do is inference, as we were discussing here, what you can do is to infer directly, let's say, the posterior distribution, right? And in that case, you will infer this. But still, I think your question is like, what happens if my data intrinsically has some error, right? So there are still ways to do this. This is like, for instance, these days, I think people use this forward modeling. So, for instance, imagine at the level of simulations, right? You will say, okay, I have some data, and this data has some correlations, and there are still some covariance explaining, the error bus or something like that. So what you might want to do is, for instance, to sample. For instance, imagine that you have, like, I don't know, some, let's say the power spectrum, right? And the power spectrum for a given k-bin, there is like some kind of uncertainty. But you know that all these models will only correspond to a given value of omega matter. So what you can do is, for a given value of omega matter, you don't have like a single value. You might want to just sample all these different things. Exactly, exactly. And you say, okay, all these models basically go to the same value. So in that way, when you train a machine learning, it's basically taking into account this error itself. And another thing that I think we will also not be talking about, very happy to discuss, is how to estimate even the error from the neural network itself, right? Because the neural network is, is still fitting, is minimizing these parameters, but still there is an error there. So there are also ways to compute these errors. So just to conclude, so usually there are two kinds of errors for when we talk about this thing. There is like the, let me see if I say this correctly, like the aleatoric error, which is basically the error just coming from, let's say, cosmic variance, that there is some intrinsic stochasticity, let's say. And then there is the epistemic error, which is really the error coming from the network itself. And yeah, there are ways to compute this, and yeah, people do this every day, so yeah. Happy to go into details.
Any more questions? So I have a small question.
Mm-hmm.
So there's a phenomenon that we can call garbage in, garbage out. How do you avoid this?
Yes. Yeah, I think maybe on Thursday when we talk about agents, we might be able to tackle
something that has no correlations. You're saying maybe this star formation rate has no correlation with cosmology, okay?
Yes, but in that case, there is not a problem. So for instance, if there is really no like a function,
yes,
it will learn that there is no function, and it's going to just predict like for instance, the mean value of omega matter.
Okay.
So in that case, there is no...
There's
a
no
network
problem.
can marginalize over variables that are not important, so
okay,
no problem in that sense.
Okay. So more questions for Paco? So let's thank Paco again for this nice lecture.